Hey everyone, today's video is about resonance and damping. So first, before we even talk about damping or resonance, we're going to explore some key terminologies that we absolutely have to know. First is the natural frequency, and it's the frequency of an oscillating system after an initial disturbance without any damping or external driving forces. So that's the frequency that a system basically likes to settle on if there was no damping or no external driving forces. So if you have a spring, you stretch it a bit and then you let go, and then you measure the frequency at which the spring oscillates after you let go. That frequency is the natural frequency. And on the other hand, driving frequency is the frequency of a periodic external force on an oscillating system. So an example of a driving forces would be, let's say you and your friend is on a swing. And you are behind your friend, and you're pushing the swing. You are providing driving force to this oscillating system, which is a swing. And therefore, you are going to change by your swinging, you're going to change the frequency of the swing. And that frequency that this swing settles on when you keep pushing it periodically, is called the driving frequency. And so there is this a graph that is pretty useful to just have it memorized. And that is amplitude versus driving frequency. Amplitude of oscillating system. Or you can call it the amplitude of the driven oscillation. Let's say this point marks F0, which is the natural frequency. And I'm going to get a ruler. Just put a dashed line where the frequency is the natural frequency. Okay. So initially, when driving frequency is 0, don't ask me why, I don't really know, but when driving frequency is 0, the amplitude is at a pretty low number. And then as the driving frequency increases, the amplitude of the driven oscillation increases, but kind of slowly. So it's like a straight line, and then it increases. And as we approach the driving frequency right here, it never, an asymptote of sorts is formed. It just goes like that. Basically, as you approach the driving frequency, amplitude reaches infinity. And one very important thing that I forgot to mention beforehand is that this graph is assuming there is no damping. So basically, this diagram is impossible. Obviously, how do you reach infinite amplitude? That's not possible in the real world. But theoretically, without any damping, the driving frequency perfectly matches the natural frequency, then the amplitude will be infinity. And then after we hit the driving frequency, as we increase the frequency more and more, it will start to obviously decrease. And as we increase it even more, it will tend to 0. And the tending to 0 makes sense because as the frequency increases, the oscillation of the system can't really catch up to the increase of the frequency, so it just tends to 0. But again, this graph is theoretical. In order to draw a realistic amplitude and driving frequency graph that is accurate to reality where damping exists, we have to draw a different graph. But first, before we draw another graph that takes damping into account, let's first define damping and all the different types of damping. So damping is just the loss of energy in an oscillating system. And there's three main types of damping. First is light damping. Second is heavy damping. The third is critical damping. Okay, I'll try to illustrate this on a graph. You got amplitude, and we have time. Okay, I'm gonna use this blue to show an undamped oscillation. In an ideal world, how an oscillation would look like. Look. Oh, hold on. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. It looks something. Oh my god, this is so horrible. Something like this, right? Frequency period is the same for all of the waves. Amplitude doesn't decrease, amplitude remains relatively same. That's how you expect it to look like. On the other hand, if you apply some light damping, it would look something like this. As you see, as time goes on, the amplitude of the wave decreases. And if you connect the crests of each sort of wave, oh my god, this is so horribly drawn. Let me redraw this. Best way to do it is, if you want to draw I drew a rough sort of sketch of light damping, but if you really want to draw a nice, accurate diagram for light damping, what you do is you draw like this kind of exponential sort of looking curve, like this. And then you just make sure that the peaks hit this. One very important thing about light damping you should know about is that for light damping, the frequency of the wave doesn't change. Only the amplitude changes, as we can see here. Now for heavy damping, I'm going to do it in green, is when there was no oscillation at all. Just kind of goes like this and stays there. This is when damping is so strong that the object doesn't even go back to equilibrium. And critical damping is when damping is just enough to get to the equilibrium. Okay, now we know about all the different kinds of damping. How do I show a realistic relation between amplitude and driving frequency? And this was where we get introduced to resonance. Resonance is when the driving frequency is very close in value to the natural frequency, resulting in very high amplitudes. But the resonant frequency is not exactly the same as natural frequency, and I'll illustrate that in this graph below. Okay, let's say we have some light damping, some like very light damping, and this is the natural frequency. Again, I'm just gonna do a dashed line. So and again, for our lightly damped graph, we're going to start off at this constant right here. As driving frequency increases, amplitude increases, and then hits a peak at about the driving frequency. This is for very light damping, by the way. And after that, our frequency just keeps on decreasing and just decreases and decreases and decreases and decreases and so on. Now for a slightly heavier damping, slightly heavier. Again, when driving frequency is 0, it will start off at the same constant. Now, the reason why, no matter what kind of damping, no matter the extent of damping, at driving frequency of 0, the amplitude is the same. The starting amplitude is the same for all kinds of damping, is because damping mainly relies on the velocity of the object that's oscillating. For example, if there's a spring that's oscillating, its main source of damping is going to be air resistance, and air resistance depends on the velocity of the spring. But at very low driving frequencies, no matter the damping, the velocity of this oscillating object is going to be 0 or very, very close to 0. And so when we're calculating the amplitude at the driving frequency of 0, we rarely take in damping into account, because the effects of damping at this driving frequency is negligible. That's why even if there's high, low, insanely low, or insanely high damping, when driving frequency is 0, amplitude will start off in a same constant. Anyways, just like we expected, as driving frequency increases, amplitude also increases. But the funny thing is, obviously, the peak is lower. That makes sense, because the system will have less energy due to more damping. So obviously amplitude is going to be, the amplitude of the peak is going to be not a lot, but quite low compared to the amplitude of the peak of a significantly lowly damped system. Okay, you might notice something strange, but we're just gonna keep on drawing for heavier and heavier, more heavily damped systems. Okay, now you probably noticed a pattern. The frequency of the peaks are decreasing. So if we had a dashed line going through all the peaks, it would look something like this. And if I extend it out, it's going to look like this curve, like a curve like this, like that. Now, why is that? That's because, I don't know if this is a valid explanation, but for me, it helps me understand. At least for quantum physics, energy is based... Wait, I think even for wave models. Yeah. Energy is related to, I don't know if I forgot if it's directly proportional or whatever, so I won't use symbol, but energy has a correlation with frequency. This is kind of more evident and more highlighted in quantum mechanics when you say E is Planck's constant times frequency, but obviously you can't use this formula here in the case of waves, non-quantum waves. But the logic is still there. Energy of a system depends on its frequency. And again, as damping increases, energy of the system decreases. And so therefore, the frequency should decrease. And therefore, the resonant frequencies are decreasing. And the resonant frequencies are the frequencies that produce the highest, are the driving frequencies that produce the highest amplitudes. I hope that makes sense. I don't